Here we are.
Say it, please. Please. Please.
I don't know. Okay. This is a lot. Now I'm
If
in
you're
there.
posting this on YouTube, you got to.
I'm all red.
Oh, happy birthday.
Okay. All right, here we go. No, this is example 3. This is from the related rate section. Gosh, this is a lot. Okay, so I did put the picture of the actual words from the problem. Okay, so example 3, we have a sliding ladder. A sliding ladder. Remember, there are a couple of tips for you. 1, don't plug in too early. 2, if you haven't done any calculus in your related rates problem, it's wrong. There is some calculus involved, or at least there should be. So if your only move here is Pythagorean theorem, you're doing 8th grade geometry, not calculus. Okay? All right, so a ladder 10 feet long rests against a vertical wall. So the first thing we want to do in related rates problems generally is draw a picture. That way we have a better idea of exactly what's happening. Okay. And that's the notes that you took about how to solve these problems. They suggested drawing a picture. So in my picture, you see the floor and you see a vertical wall and you see a ladder, and the ladder happens to be 10 feet long. It says if the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So again, we've got a rate, which tells me that's a velocity. That's a derivative of something. That's the bottom of the ladder sliding away from the wall. So that's going to be this length right here along the bottom. So what could we call that? Floor. Sure. How about x? It's horizontal, right? So this distance here is going to be x.
Like that was obvious.
Sometimes I just have to try so hard to be nice. Sometimes I look at it and I'm like, yes, floor, wall. How about x? So if this is the change in that distance, we might call it what? X prime, yes, f prime of x. How about dx dt? The change in x with respect to time. The change in x we could call it floor prime. Yeah, sure. The change in x with respect to time. Okay, how do I know it's with respect to time? Because in the rate they gave me feet per second. Change in x with respect to time. And it says it's sliding away from the wall, so I'm going to think that's a positive change. dx dt equals 1 foot per second. The question is, how fast? How fast? So what are they asking? At what speed? At what velocity? At what rate? Okay, so we're looking for a derivative. How fast is the top of the ladder sliding down the wall? So we've got x changing as the ladder slides out. We've got y changing as the ladder slides down. Good. As the ladder slides down. So we're looking for dy dt. That's what we want to know. How is the ladder, or the y height, the wall, how's that changing as this ladder slides down? Okay, so you can imagine it's going like this, right? How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So now what have they given me?
6.
They've given me x. They've told me x is 6 feet from the wall. So when x equals 6, that's what instant we want to know what's the rate of change in y. Question, is the rate of change in y always the same? Would it matter if x was 6? Would I get the same thing if x was 7? Think about it.
No.
So is the dy dt, the rate of change that the ladder's coming down the wall, is that going to be the same at x equals 6 as it would be if x was 7?
No.
No, why?
It's gonna get faster.
Gravity. It's getting faster. It's accelerating. We know things. Yay! Okay. So the ladder slides away from the wall at a rate of 1 foot per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet? We've got it going on here. What do we not know?
But why wouldn't the X6 be on the second image and not?
Okay, because on the first image is distance, length of the wall. The second image is a velocity triangle, and it's different. Okay. When x equals 6, what's y over here? Could we find it? Could we figure out what number y is? We could do that. How? Okay.
Isn't it an 8?
8.
It's probably an 8.
Yeah.
6, 8, 10. Feels about right. You could check that. 36 and 64 is 100. Right? So y equals 8 in this moment. What relationship did you use to figure out that y equals 8? Pythagorean theorem. We've got a right triangle situation here, don't we? We have a situation where we know x squared plus y squared is equal to c squared. What's c?
The hypotenuse.
Which in this case is 10. So 10 squared would be 100. X squared plus y squared equals 10 squared, which we're calling 100. Is that 10 changing? Do I need to let that be a variable?
No.
Why not?
The ladder.
It's a ladder. The ladder's not getting shorter, right? So that 10, that's a constant. We get to use it, okay? This is not a situation where we have substituted in too early because that 10 is 10. It's a hard 10, okay? How might we go about finding dy dt given this situation, this relationship? I don't know where I'm going to get that stuff.
Differentiate x.
Here's where the calculus comes in. We find dy dt by taking the derivative of our relationship here, okay, with respect to time. So I'm going to differentiate each term. If it's x squared, what's the derivative? 2x dx dt plus 2y dy dt equals 0. Everybody okay so far? Okay. What do I want? What do I need by itself? We're looking for dy dt. We're looking for dy dt. We could plug in right now, or you could solve for dy dt and then plug in. It doesn't matter one way or the other. What do you want to do? Solve and then plug in? Okay. So I would subtract 2x dx dt from both sides. So 2y dy dt is equal to negative 2x dx dt. Divide by 2y. So dy dt is equal to, those 2's are going to cancel, negative x over y times dx dt, or negative x dx dt all over y, either way. Now we can plug in. Dy dt is equal to negative 6 over, what's y when x is 6? 8. Times dx dt, which is 1, and that's a positive 1. That side's getting longer. So when we reduce that fraction down, what do we have? Negative 3/4. What? Feet per second. Feet per second. So if we were going to close this out, what would we say?
At 6 seconds. No, not 6 seconds. When x equals 6.
By why? So
We're shrinking by 3/4.
right, shrinking by, so you can handle the fact that it's negative. That means it's getting smaller. You can say y is decreasing by 3/4 of a foot per second. Or you could say y is changing by negative. You don't have to say both. If you do say both, you're canceling it out. Okay, so you wouldn't say it's decreasing by negative 3/4. You would say it's changing by negative, or it's decreasing by positive 3/4. Okay, so your verb of choice kind of tells the story there. Any questions here?
That problem is more straightforward than the other.
More straightforward than the others? Okay, fair. Cool. Here we go. Example 4, a water tank. You're always going to have a water tank problem. Just saying. You're going to have a water tank problem. Sometimes the water tank is a cone. This one's a cone. Sometimes your water tank is a trapezoid. In some of your homework questions, they're trapezoidal prisms. Yeah. Lots and lots of water tanks here. Let me look through your homework right quick, and I'll tell you what problems not to worry about. Yeah. You're not going to like 22. 22 is a really good problem, but you're not going to like it. So I wouldn't spin out on 22 if you don't want to. And then I think that you're not going to like number 32. 22 and 32. Yuck. 31's pretty good. Okay? In addition, I have a packet of circuit problems, and the circuit problems for this unit are a lot more straightforward than the textbook problems. So if you'd rather do the circuit problems, that's why I printed them. Okay, they're a little nicer. You should do the circuit problems. I just don't know if you want to do both. Okay, but if you're going to pick one or the other, you should do the circuit problems. Are we clear? Okay. All right, example 4. A water tank has the shape of an inverted circular cone. Inverted circular cone. So we're looking at something like this. You know those little snow cones that you had when you were a little kid? Yeah.
Party hat.
It's like the little cup. Yep. Base radius 2 meters and height 4 meters. So your radius is 2 meters. Your height is 4 meters. Water is being pumped into the tank at a rate of 2 cubic meters per minute. What in the world? What's that? 2 cubic meters per minute.
Every minute.
It's the rate of change of what? Of volume. That's the amount of water being pumped into the tank. So this is a volume rate of change. So what letters might I want to use here to talk about this thing? dV dt. This is the rate of change of volume. How do I know that? One, it's measured in cubic stuff. Usually that's volume. 2, it says rate. That's how I know it's a derivative. Okay. Find the rate at which the water level is rising. So the rate at which the water level is rising. What am I looking for?
Derivative of volume. Yeah.
We have derivative of the volume. We said that was 2 cubic meters per minute. Yeah, find the rate of change of height. Find the rate at which the water level is rising. So as they're filling it with water, right, we're looking for how's the height changing? So we're looking for dH dt. Is that making sense as to why that's what we're looking for? And they told me when the water is 3 meters deep. When the water is 3 meters deep. So deep, what number did they just give me? Deep. Height. So they just told me H at the moment when H equals 3. The height of the cone is H equals 4, right? But the water level isn't consistently 4 unless it was filled to the brim. So this is at the moment when H equals 3. You following that? Okay. So we need to find the volume of the cone. That's going to be our relationship here, because they've given us derivative of volume. So we need to be thinking, okay, what's the formula for volume of a cone? Do you know it?
Yeah, it's a third pi r squared times the height.
It's 1/3 pi r squared times height. Yesterday we did, or the day before, sphere is 4/3. A cone is part of that. Right? So volume of a cone is going to be 1/3 pi r squared times the height. 1/3 pi r squared times height. Okay. We're looking for dH dt. We have dV dt. We don't have any information on the RDT, the change of radius. We don't have that here. Can y'all tell? So when we go in here and we take the derivative of the volume, we're going to have a dRdt piece. We don't want it because we don't have anything about it. We don't have any information to sub in. So instead of R, we're going to substitute R out. So we're not going to have a radius in our formula at all. We need H because we have information for H. We have when H equals 3. We're solving for dH dt. H gets to be a part of this problem. Okay? R doesn't. So how can I remove the variable R and bring in an H in its place?
When they're the same.
Okay, but look at the relationship. The radius is 2 and the height is 4. It's half. They're not ever going to be the same, but I could say that R, how about 2R equals H, or R is half of H? So if I swap out R here in this formula, and I can swap in H, then I only have volume and height as variables. Are everybody seeing what we're doing here? Okay, it's a pretty bold move, but it's nice. It works. So now we have 1/3 pi, and instead of R, we're going to put H over 2 squared times height. And then let's simplify that before we take its derivative. Okay, so volume is 1/3 of pi, and then that H over 2, if I square a quotient, becomes H squared over, anybody? 4. If I square a quotient, I square the top and the bottom. So H squared over 4 times H. Yeah, so now I have volume is, can I put the 1/3 and the 4th together?
Yeah.
Could I call it 1/12? Are y'all good with that? So 1/12 times pi times H cubed. Now this one feels like I could take the derivative. Okay. So when we do that, now we're going to take the derivative of v, which we know to be dv dt, equal to, remember that this 1/12 and pi, they're all constants. You could call it pi over 12 if you wanted to. But that part stays. That doesn't go away. So you have pi over 12 times, and now we're going to differentiate h cubed. 3h squared dH dt. And the dH dt piece is what we're actually looking for. We could divide everything over here, right? The derivative of volume with respect to time is 2. Do y'all want to plug in and then solve, or do you want to solve first? What's your call? I think it's nicer to to plug in first, because some of these numbers may cancel. right? So dv dt in this case is 2 equals pi over 12 times 3 by, when h is what? 3 squared times dh dt. $27, right? 3 times 9, that'd be a 27 over 12. So 2 equals 27 pi over 12 times dh dt. Did you see where the 27 and the 12 came from? I have 3 times 3 squared, which is 3 times 9, 27, all over 12. Now, you could just multiply both sides by the reciprocal. That would get rid of it. So if I multiply both by, 12 over 27 pi?
Can we make that 24 over 27?
Sure. Those are going to cancel. Okay, so I'm hearing 12 times 2 over 27 pi. That's going to be 24 over 27 pi. I would put that in a calculator at this point. You could reduce it. Both 24 and 27 are divisible by 3. So you can have an 8 over 9 pi.
Almost pi.
Anybody get a number? 8.283? What?
It's meters, cubic meters. Oh, no, it's just meters.
Meters per
Yeah.
minute. So dH dt equals 0.283 meters per minute. So this problem is only iffy in this part right here, where you're trying to swap out a variable. Okay, this right here. See in that relationship. The reason we know to do that is because they didn't give me any information for R. I don't have any info for dr dt. Okay. I think you like that one less than the other one. That's fair. That's fair. Let's see if we can get another one. We may save the last one for Monday, and then we'll try to wrap up. But I would prefer if you would do the circuit or get started, do something over the weekend on this topic so that it's not just brand new on Monday. All right, it says car A is traveling due west at 50 miles per hour. Car A is traveling due west at 50 miles per hour. Car B is traveling due north at 60 miles per hour. Both are headed for the intersection of two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? So we have to draw a picture. Okay. I want you to imagine that there is like an intersection like this. And they're approaching this place. Does that make sense? So car A is traveling due west at 50 miles per hour. So I'm going to let this be car A. They're traveling due west at 50 miles per hour. So what is the 50 miles per hour? That's the rate. That's the rate. So let's let that be dx dt. It's going to be negative 50. Initially, when I worked this problem, I thought it was negative 50 because it was west. But I remembered this is calculus, and they don't so much care for directions as much as they care that this distance is getting smaller. Can you understand that? This distance between car A and the point of intersection is shrinking. Because that distance is shrinking, we're using negative 50 miles per hour. Okay. Then we've got car B traveling north, so going this way. And I let this be dy dt because it's vertical. And again, that distance is shrinking. Even though they're going north, it's still going to be a negative because we're not so concerned with direction as we are that the side length is shortening. This is at 60 miles per hour. Negative 60 miles per hour. And the question is, at what rate are the cars approaching each other? So what we're looking for is the distance between the cars. At what rate is that distance becoming shorter? That's the hypotenuse. That's the hypotenuse.
You can always draw a right triangle.
So at what rate is this distance between them changing? So what are we looking for? dh dt, if h is the hypotenuse. We've used x and y. Let's go with z. Let's go with z as that third side length. So we're looking for dz dt. This is where the temptation comes in to do Pythagorean theorem. Because it feels like I've got three sides of a right triangle. Why can't I not say that dz dt squared is the square root of dx dt squared and dy dt squared? Why is that not true?
It is right now, but that's the derivative.
Right, because these are all changing. These are all changing. Hence the calculus, right? So at what rate are the cars approaching each other when car A is 0.3 and car B is 0.4? So they've set up a relationship for us is what?
X and Y.
X and Y. And what does your gut tell you when we have a right triangle? How can we find the missing side length? We want to do Pythagorean theorem, right? So our relationship here is x squared plus y squared equals z squared. That is the geometry behind this problem, okay? Now we have to do the calculus, which is to do what? Take the derivatives, okay? Derivatize, yes. So when we do that, we're going to do the same to both sides. What do we have on the left?
2x dx
2x dx dt
plus 2y dy dt equals 2z.
dz dt. Ah. Cool. You note that everything has a 2 in front? Lose them.
Take it all.
Lose them.
Go on.
We do know what to plug in for x. They told us car A is 0.3 miles and car B is 0.4 miles. So there's our x and our y. We also have dx dt and dy dt. So out of all of this, what's the only thing we don't have? We don't have dz dt. We're solving for it. We also don't have z. Can we get it?
Yeah.
How?
I think we can.
Yeah, we can just do regular little Pythagorean theorem to figure out what z is. We know car A is at 0.3, car B is at 0.4. So anyone take a guess at z?
5.5.
Feel like that's a little 3, 4, 5 triangle.
Yay.
Okay. So x is going to be 0.3 times dx dt, which is negative 50, plus y, which is 0.4, times dy dt, which is negative 60, equal to z, which is 0.5, times dz dt, which is what we're looking for.
Divide by 0.5.
Yeah, just take this whole side, both sides, and divide by 0.5. Did you use your decimals?
Yes.
We got negative
Oh, never mind. I didn't use the one at the bottom.
Negative 78 what?
Let me retype it.
Miles per hour. So what does that tell me?
That the distance is closing by 78 meters per hour.
Miles per hour. Yeah. So they're getting closer together at a rate of 78 miles per hour,
Yeah.
which is not what you would get if you had done the square root of 60 squared and 50 squared. It's not the same number. Cool? Questions on this one? No? So we only lack one example. Let me pass out the circuits. Get started on those. We'll do the last example on Monday. We can circuit on Monday. Okay, but get started. Get started over the weekend.